Hey, you're hanging with Hussick again. The video here is going to be on Ksp and solubility problems, part 1. So we're going to look at sort of how those two intersect and solve a couple problems using Ksp and using solubility of different salts. Okay, let's start with this one. The Ksp for lead 2 sulfate is 1.8 times 10 to the minus 8. What mass of this salt would be present in 100 milliliters of a saturated solution? Okay, so we'll try and work backwards, see what we're given. So we're going to try and find what mass would be present in the solution, okay? And it's going to be in a 100 ml solution, but it's going to be a lot easier if we first try and figure out what the concentration of lead sulfate will be in moles per liter, okay? And then we can basically divide that by 10 and convert that into milliliters easily enough. And we can convert that moles into mass using the molar mass. Okay, so it won't be too difficult for us to do that conversion, but we first need to figure out, or the easiest thing to figure out first will be what's the concentration of lead 2 sulfate in the standard unit of concentration, which is moles per liter. Okay. The other thing we'll need to know the formula for lead 2 sulfate. So if you need a little review on how to write formulas from the name, do that for yourself. But this is going to be an ionic compound, of course. It's going to create an ionic solution. And the formula for lead 2 sulfate, okay, would be Pb2 plus. The sulfate ion has a 2 minus charge, so that's going to be the formula for lead 2 sulfate. Why does that matter? Well, if we're going to need the molar mass to do that conversion from moles to grams, we're going to have to find the molar mass for lead 2 sulfate. And if you do the math on that, the molar mass for this is going to be 303.3 grams per mole. Lead's very heavy, so it's a pretty big molar mass. All right, so what do we know about this thing? Well, we know that if we're using the Ksp value, and again, you either have to be given these in the question, or you have to use the table of the data table, the table of values that you have to find these KSPs. If you're given that, it tells you right away that, well, we're dealing with a system in equilibrium, right? This has to be in equilibrium. That's the rule for any use of K equilibrium or KSP, all that kind of stuff. Okay, it has to be in equilibrium to use it. Okay, so we know this is going to be in equilibrium. We also know that because it's talking about the saturated solution, which is also in equilibrium. So that should all three of these things should kind of evoke the same outcome for you. We're dealing with this system in equilibrium. So what's it going to look like when it's in equilibrium? Well, we know that when this system is at equilibrium, we can basically use this chemical equation to describe it. Okay, it's going to be the lead ion and a sulfate ion. Okay, we know that whatever value of this we've actually dissolved is going to produce lead 2 plus and sulfur ion in a 1-to-1 ratio. So basically we're going to dissolve X amount of this, and we're going to gain X amount or X moles of each of those respectively in response to that, right? So hopefully that's a concept you understand. What can we do with that? Well, because we're given a Ksp value, and we know we can also model this system with this mathematical Ksp expression, the solubility ion product constant, we know that we can take the concentration of lead 2 plus to its exponent coefficient, which is just a 1, and multiply it by the concentration of sulfate when it reaches solubility raised to its coefficient, which is also 1, and multiply them together to get Ksp. Ksp is given to us. It is 1.8 times 10 to the minus 8. And the key to solving this question is that since both of those have the same value, we only have one variable to solve for, so it's going to be x squared like that, right? It's x times x, x representing concentration of lead 2 plus, x representing concentration of sulfate. So we multiply those together, we're going to get x squared equals 1.8 times 10 to the minus 8. So if you solve that by taking the square root of both sides, it's a perfect square, you're going to get that x is equal to 1.34 times 10 to the minus 4. Okay? Okay, so let's interpret this answer. Like, what's it actually mean? Well, it means this essentially was the concentration of each of those ions when it's dissolved. And it means that this was also the concentration of lead sulfate that we're able to put into the solution. So it's kind of interesting that way. It's like if you said what's the concentration of lead sulfate or what's the solubility, you might describe it as that, right? It also means that each respective ion has that concentration. So when you multiply them together, you get that Ksp value. So let's go interpret that. This is basically that thing we were after at the top. Okay, this is moles per liter. So if we've got 1.34 times 10 to the minus 4 moles per liter of the lead sulfate, we can then multiply that by the molar mass of 303.3 grams per mole, and that's going to translate that into grams per liter. So once we have that grams per liter value, let's just do it all in one step. Then we can turn it into grams per milliliter by saying we're going to multiply that by the 0.100 liters. That's, 0.1 of a liter is 100 milliliters. I'm having trouble with my decimal place here. There we go. Okay, so then if we do that all in one shot, you're going to get 1.34 times 10 to the minus 4 times 303.3 times 0.1. It's going to give you 4.1 times 10 to the minus 3 grams. And that's how much grams since liter are gone, and we use that value. That's how much grams it would be in 100 milliliters. Okay, let's have a look at this one. In this one, we are asked what is the concentration of the copper 2 plus ion in a saturated solution of copper 2 sulfate. Okay, so what do we know about this? Well, since it claims it's a saturated solution, we know that we can describe the situation like this. Okay, we would have the copper 2 plus ion and the sulfide ion aqueous, existing in equilibrium with just whatever little tiny remnant of copper sulfide solid was there. Okay, so if we want to figure out what that ion concentration is, the value we need is, of course, the Ksp. So we'd have to refer to our list of Ksp values, and hopefully this one is in there. But the Ksp value for this copper 2 sulfide, we'd look up and see that the Ksp is equal to 6.0 times 10 to the minus 37. My goodness, this is a very insoluble salt. Okay, so there's not going to be much in there. This is a really small number. So then we'd say, okay, the Ksp expression is concentration of that to the exponent 1, so forget it. Concentration of that multiplied to the exponent 1, right? We've got just ones right there. Okay, and then we could do 6.0 times 10 to the minus 37. How do those two concentrations compare? This is the one big kind of leap here. How does the concentration of copper 2 plus relate to the concentration of the sulfide ion? And you should realize they're going to be the same, because you get X amount of that and you get X amount of that for every X amount of that is put into the solution and dissolves. So really, this is again solving a perfect square. We're going to take the root of both sides. We're going to find out that X is equal to 7.75 times 10 to the minus 19, and that's going to be the concentration of the copper 2 plus ion, or the sulfide ion if it asked for it, in that saturated solution of copper 2 sulfide. In addition to that, it would also be the solubility of copper 2 sulfide, because it's the same 1 to 1 to 1 for all of them. So this really is the concentration of either ion in this case, or you would say it's the molar solubility of copper 2 sulfide. All right, let's look at one that goes the other way. This one's asking what is the Ksp. So presumably we can't just look this one up on our list, or it's not on our list or something, and not every salt in the world's on there. But what's the Ksp of calcium fluoride if a saturated solution of it has a calcium 2 plus ion concentration of 2.1 times 10 to the minus 4 moles per liter? So we know it's at We know it's saturated solution, so we know it's at equilibrium. Calcium fluoride looks like this. It would be CaF2, because fluoride is a halide ion with a -1 charge, and calcium's 2+ as an alkali earth metal ion. So we know it's going to exist in equilibrium. That's the solid. Sometimes I forget to write that. It's going to exist in equilibrium with these two ions like this. And we're going to need 2 of those F- ions for every 1 of those calcium ions. So that means, like, if we dissolve amount X of calcium fluoride salt, it's going to produce X amount of the Ca2+ ion, and it's going to produce 2X amount of the fluoride ion. So that means if we put it into the Ksp expression, it's going to be the concentration of Ca2+ at equilibrium, or in a saturated solution, which we have, okay, multiplied by the concentration of the F- ion, which is actually going to be twice as much as X, right? And it's going to be squared. So this is kind of a double whammy effect. When you have a coefficient 2, remember, it actually manifests that itself in 2 different places. It both means you get twice the concentration here, and you square that. All right, so it's kind of like a wacky effect, but what we have then is the Ksp is going to be 2.1 times 10 to the -4. Okay, because that's what they gave us for the calcium ion concentration. We're going to have to multiply that by 2. Okay, so it's going to be times 2 times 2.1 times 10 to the -4. Okay, and then that whole thing is going to be squared as well. So that's the math we're going to have to do on that. And if you do all that, you're going to find out it's 3.7 times 10 to the -11. Okay, so the Ksp for this salt is 3.7 times 10 to the -11. Maybe I'll just put a little green highlight in there for you to see that's where that one went and that's where that one went. All right, in this one, we're going to work the other direction. So, we've got the Ksp of copper 1 bromide being 6.3 times 10 to the -9. Again, that has to be given to you or found in a table. And what is the solubility of this salt? So I like this kind of question because it highlights that Ksp and solubility are not exactly the same, although they're related by these models that we look at. Okay, so we should first realize that copper 1 bromide is going to have the formula CuBr, right? Br, the bromide ion, is a halide ion with a -1. And you got copper 1 bromide CuBr. So it's going to exist in an equilibrium because we're talking about Ksp, which means we're dealing with equilibrium situation. It's going to exist in equilibrium like this. There we go. So for every 1 unit of the salt that is dissolved, we're going to get 1 unit of the copper 1 ion and 1 unit of the bromide ion, right? As well, then, we can go ahead and put the Ksp expression down there. We know that Ksp then for this will be the concentration of copper, copper 2+ the first time by mistake, copper times the copper 1 times the bromide, okay? So we're going to be like that. We also know then that since Ksp is 6.3 times 10 to the -9, all right, that we can sub that in and solve for X. We know that X is not only going to be the concentration of each of these, but it's also going to be essentially how much moles of that we put in. So X will also be the solubility of the copper 1 bromide, you see, because it's its maximum amount that we could dissolve in there. So let's see what we get here. We'll take the root of both sides. We're going to find out that X is equal to, let me see what I got there, 7.9 times 10 to the -5. 7.9 times 10 to the -5. Okay, and so that's also going to be, as well as being the concentration of each ion, that's going to be the moles per liter, the concentration of copper bromide that would have went into solution. So therefore, we would say the molar solubility, or the solubility of copper bromide, is 7.9 times 10 to the -5 moles per liter. Now in this one, you just have to watch out for your x's. It's all 1 to 1 to 1. In a different situation, just watch out for your 2s or 3s or whatever might be out there for coefficients.